So we are doing gas stoichiometry. So when you talk about stoichiometry, that means a couple of things. That means you're dependent on a balanced equation because you need the coefficients for the mole to mole ratio. So on these, we're going to be using those things. So you'll have to have a balanced equation. And then at some point in the problem, you'll be using your mole to mole ratio. On some of them, you'll also be using the ideal gas law along with it. All right, get caught up there. All right, so we'll talk about molar volume whenever you're at STP, and also whenever you're not at STP. It's a little bit easier whenever the gas is at STP. Remember that only gases can go into any of the ideal gas laws that we've learned. So you may have some compounds like an ionic compound, you may be given some information about it, but that cannot go into the problem that you might be working on. Only the gases can go into the gas law. So the molar volume is the volume of 1 mole of a gas. And it depends upon the temperature and the pressure of the gas, not of its identity. And at STP, at standard temperature and pressure, all gases have the same molar volume, and that is 22.4 liters per 1 mole. So if I could count out 1 mole of helium, even though it's very light, and 1 mole of, let's say, xenon, which is going to be much heavier, they still both would occupy 22.4 liters if they were at STP. So that it becomes a conversion factor, and it's on your pink sheet, kind of right there in the middle, under your constants and your conversions. And it becomes a conversion factor that shortens the process, shortens these problems, but it only works if you're at STP. If you're not at STP, it does not hold true, and then you're going to have to use the ideal gas law. The connection between the stoichiometry and the ideal gas law is going to be moles. So either I'm going to use the ideal gas law to find out how many moles of gas I have, and then use that information in the stoichiometry problem, or use a stoichiometry problem to find out how many moles I have, and then put that into an ideal gas. So it's a combination of those. So let's look at, first of all, just starting in the easier problem. It says, what volume of hydrogen is produced by the reaction of 36.5 grams of magnesium and excess aqueous hydrochloric acid at STP, standard temperature and pressure. So this is at STP, so that means I can use that 22.4 liters per 1 mole if I need to. Now we have to have a balanced chemical equation. So it said magnesium, which is a solid. You should be able to figure that off the periodic table. Hydrochloric acid, and it tells you right there that it is AQ. And this is a single replacement reaction. The magnesium is going to replace the hydrogen. So I end up with hydrogen gas plus magnesium chloride. So magnesium chloride, does anybody know what state that would be in? It's an ionic compound. Perfect. All ionic compounds are solids. You might want to jot that down somewhere. So that's whether it's just a metal and a non-metal, or it could be a metal and a polyatomic ion, but those are always solids. And then I think we need to put a 2 right here in front of the hydrochloric acid to get it balanced. So I only have one gas in there directly, hydrogen. That's the only one that could go straight into something like the ideal gas law. So what I do have is my given, which is 36.5 grams of magnesium. So that's my given. And I want to get to volume of hydrogen. So I want to get to liters of hydrogen. It is at STP, so that means I could use this 22.4. So that means if I could get to moles of hydrogen, then I could use that conversion factor to get me to liters. So that's what my goal is. I want to get to moles of hydrogen so I can use that conversion factor. So now we just start working through our problems. Here I have grams of magnesium. Grams isn't helping me, so I need to go from grams to moles of magnesium. So you would use the molar mass and magnesium straight off the periodic table, 24.31 grams per 1 mole of magnesium. And then I would keep on following my units. If I'm moles of magnesium here, I have to be moles of magnesium down here. Nothing about grams in this box. So this is my mole to mole ratio, which we said we would be using in these problems. There's 1 mole of magnesium, which is my known, for every 1 mole of hydrogen, which is my unknown. That's what I'm trying to get to. So we're almost there, because if we stopped right there, if I canceled out my units, the only thing I would be left with was moles of hydrogen. We don't want to be moles of hydrogen. We want to find the volume, the liters of hydrogen. And then that means I can use this last conversion factor to get me there. So if I'm moles of hydrogen here, I have to be moles of hydrogen down here. And that conversion factor says 22.4 liters per 1 mole. The 22.4 always stays with the liters, and the 1 always stays with the moles. So now the mole canceled, and there would be my problem, and I would multiply across 36.5 times my 22.4. Come back and divide by 24.13. If you don't have a calculator, please get one. And how many sig figs? 3 sig figs, exactly. So I think you should have gotten 33.6 liters of hydrogen. It's not quite like stoichiometry. I can't say these are always going to be 3 steps or 2 steps or 4 steps. It's going to depend on what you're looking for. So that's why you have to work through your units. But a couple of hints here. Number one, that it said STP. That's going to be a hint that you're going to use that 22.4. And then you're going to have to think how you can get from your known to your unknown. And once again, that's going to be through that mole to mole ratio where you look at your coefficients. All right, now let's look at a couple where we don't have STP conditions. So then it's going to be a little bit longer. We're going to have to use stoichiometry, and then we'll also have to use the ideal gas law. A couple of people in my other classes asked me where that 24.31 came from, and that's just the molar mass of magnesium. So it's just this element by itself. Any other questions on where any of the numbers came from? All right. So here we have another situation. And I just need to rewrite my formula. Not my formula, my equation. All right. Same equation, and that is balanced. Okay, so let's see what we got going on now. What volume of hydrogen? So once again, my unknown is going to be liters of hydrogen. That's going to be my unknown. It's supposed to be 2 question marks. Is produced by the reaction of 36.5 grams of magnesium with excess hydrochloric acid, and then I have a temperature and I have a pressure. It does not say that I'm at STP, so there's not going to be any of that 22.4. We're not going to be using that because we're not at STP. So if I want to find the volume of hydrogen, the way that we've been doing that is through the Iodine Gas Law. PV is equal to nRT. So if I look at that, I have torr, so I have my pressure. My R we always have because that's a constant, and I have my temperature. But I don't have moles, so I'm lacking 2 things at this point, so I just can't take those numbers and start filling them in. I can't put grams into that formula, and besides that, that's grams of magnesium, which is a solid. So can I, though, get from grams of magnesium and figure out from that, using my balanced equation, how many moles of hydrogen I have? We can do that, right? That's going to be a gram to mole problem. So that's going to be 3 steps. So I'm going to start with my given 36.5 grams of magnesium, and I need moles of hydrogen so I can put it into my ideal gas law, finish it up. So we've already used that 24.31 grams per 1 mole of magnesium. Neither magnesium nor hydrogen have a coefficient, so that means it's a 1-to-1 mole ratio. All right, everything canceled. I'm left with moles of hydrogen, which is what I need right now. So just do 36.5 divided by 24.31. And that would be 3 sig figs because of the 36.5. So 1.50 moles of hydrogen. So now if I come back to this, now I do have my N. So now I have everything except volume. So now I would use this information and put it into my ideal gas law to get the volume. So we go back, our pressure was 730.5 torr. My volume is what I'm trying to find. My moles is what I use my stoichiometry for, 1.50 moles. I have to just do them. Since we're in torr, we wouldn't use a 0.0821. We would use 62.4 would be my R. And then my temperature, I would take 25 plus 273, which would give me 298 K. Kind of ran out of room to put them. All right, so we're solving for V. So you're going to multiply these three and then divide by your 730.5. What did we get? I'm sorry. Anybody? I got 38.2. And then my units are liters. If you're not getting that, if you've got this whole thing set up, because there's a couple of people in here that'll have it all set up, but then when they put it in their calculator, they're doing something wrong. So to me, like, I would be really frustrated because it's like you've done all the hard work and then you're missing that point. So we really need to go over that. Does anybody not get that answer or struggling with getting that answer? All right. So that would be an example of when I use stoichiometry first and to get my moles and then put it into my ideal gas law. We're going to add on, hopefully you have a little extra work places to do some work at the bottom. I'm going to add on another problem. All right, first of all, I'm going to give you your equation. Calcium chlorate what would that be? Solid, liquid, or gas? Solid, perfect, because it's an ionic compound. It's a metal plus a polyatomic ion. And then that decomposes into calcium chloride, which would be a solid, liquid, or gas? Solid, another ionic compound. And oxygen, which would be what? Gas. And then we needed a 3 in front of that to balance it. So these are our conditions. Sorry, y'all. We're at 301 K and 1.9 ATM. And we have 8.7 liters of high oxygen. And what we're trying to find out is how many grams of this calcium chlorate. All right. So we're going to do a combination of, because we're not at STP, so we're going to do a combination of ideal gas law and stoichiometry. I want y'all to tell me which one am I going to do first. I do an ideal gas law first or stoichiometry first? Stoichiometry first. Okay. So if I'm doing stoichiometry first, then what's going to be my given of all these things that I have? You have. What are you going to get started with? I'm sorry? If we got started with 8.7 liters, what in stoichiometry would we be able to use to convert that to something like moles? Because we can't use 22.4 because we're not at STP. And we don't have density, so that wouldn't help us. So what about instead if we used ideal gas law? Because if we use the ideal gas law, we have everything except for moles of oxygen. We could use ideal gas law to find moles of oxygen. And then we could go from moles to grams to get it to the grams of our solid. So on this one, that's how we're going to have to go. If we would have been at STP, Harima, then yeah, we could have started with that 8.7 and we would have never had to use the ideal gas law. But we don't have anything that we can get out of that liters. with the information that we're given. But we do have everything we need to use the ideal gas law. So my pressure is 1.9 atm. My volume is 8.7. And remember, all this information is about oxygen, which is a gas, 0.0821. And then my temperature is 301 K. All right. 2, 1. And because of that 1.9 atmosphere, we're going to have 2 sig figs at this point, and also at the end. So I got 0.67 moles. We're good with that so far? Now, and that's moles of oxygen. So now I'm going to go from moles, and I want to get to grams of this calcium chlorate. So it's a mole to gram problem. So that's going to be 3 steps. So now I have something to start with, my 0.67 moles of oxygen. And if you just put 0.67, that would still be correct. That 0 is just a placeholder. I need to get from moles of oxygen to my calcium chlorate. So this is where I'm going to use my mole to mole ratio. So I have 3 moles of oxygen because that's my coefficient for oxygen for every 1 mole of this other thing that I'm tired of writing today. I want to get to grams. So I follow my units. This is moles. If I have grams, that means a molar mass. So you would have to figure out the molar mass of that CaClO3. But instead, I'll just give it to you. 206.98 grams per 1 mole. So my moles cancel. And then I'm going to multiply across. Divide by 3, and it'll still need to just be 2 sig figs. You got 46 grams, and that would be if you don't need to write this, but I'm gonna of my solid, because none of those numbers had to go into the gas law as far as that being a solid. So like I said, these are kind of just ones that you really have to practice on, because I can't say, oh, it's this many steps, or oh, it's that many steps. Let's look at number 1 in the practice, because it's kind of been a pain for everybody, and it's kind of like just an oddball problem. Let's see if I can get to that. And we're not going to have a separate quiz on just this. You'll see it on the test, and it's pretty heavy in the test since we didn't have a quiz on it. The test is multiple choice mainly, and then I think a couple of, I don't have practice in here. What did I do? Yep. Nope, I don't have stoichiometry. Let's see. Let's look. So I don't have to do that anymore because everybody's here. And then a couple of problems. Let's see, did I put you somewhere? One other place. Y'all go ahead. Y'all skip number 1 and move on to number 2, and I'll see if I can find it on here in your practice. And of course, as soon as I said that, then I found it. So.
And it's always like whenever you're trying to find a Lego piece, you find it 10 times whenever you're not looking for it, but when you are, you can't find it once.
There we go. Okay, so I found it, of course. So, like I said, this one is kind of a kind of just an oddball one. And usually I'm not going to put an oddball question on a quick test. Okay, so this one for the reaction, you got your nice balanced equation. It tells you that everything is a gas. How many liters of water can be made from 5 liters of oxygen gas and excess hydrogen at STP? So since we're at STP, we will be able to use that 22.4 liters. So now I can use this as a given because I have a way to get out of liters. So that's going to be my given, liters of oxygen. And I want to find out how many liters of H2O. So I have 5.0 liters of oxygen. Anytime I have liters and we're at STP, then we're going to use my 22.4 liters per 1 mole of oxygen. Okay, then I continue to follow my units. If I'm moles of oxygen here, I have to be moles of oxygen down here. I have to have a way to get from my known to my unknown. So this is when I'm going to be using my mole ratio with my coefficients. So for oxygen, I have 1 mole. And for water, I have 2 moles. So if I stopped right there, I would know how many moles of water, but I don't want how many moles of water. I want how many liters of water. So what are we going to have to use in that last conversion box to get us from moles of water to liters of water? 22.4 liters per 1 mole. So it seems like you did use it twice, but this time it was with regard to oxygen, this time with regard to water. But that's kind of an odd problem where you would use that 22.4. But if you're at STP and you're doing stoichiometry and you need to get out of the liters, then that 22.4 is when you're going to come. And you should get 10.0 if I've done my math correctly. Righty. Y'all got about 10 minutes. Yes, ma'am.
Where did you get the 5.02?
No, 5.0 liters.
Oh,
Right here. Yeah, that's L.
yeah, that's confusing.
Sorry. All right. If y'all have any questions, let me know.